Hello, everyone. Today, we begin a fascinating chapter called Data Handling and Presentation. Every second, the world generates unimaginable amounts of data. Cricket statistics, weather predictions, population growth, traffic density, financial markets. But raw numbers alone are useless. The real power lies in extracting patterns hidden inside them. Mathematics calls this process data handling. Suppose you ask 300 students about their favorite sport. You now possess data, a collection of observations and facts. But here's the problem. If the responses arrive as a gigantic random list, your brain struggles to identify trends instantly. Human intelligence is powerful, but organized information is exponentially more powerful. This is why mathematicians organize data. One of the fastest methods is tally marking. Instead of repeatedly counting individual observations, data is grouped efficiently. The fifth tally cuts across the previous four, forming compact packets of 5. Simple idea, massive advantage. In real surveys involving thousands of observations, tally grouping dramatically reduces counting errors. Once data is organized, something fascinating begins to happen. Patterns emerge. Suppose shoe sizes in a class are recorded randomly. After arranging them in ascending order, the smallest value, largest value, repeated values, and dominant patterns become instantly visible. This repetition count is called frequency. Frequency reveals popularity, concentration, dominance, and trends. In advanced mathematics and statistics, entire prediction systems are built on frequencies. But tables still force the brain to read line by line. So mathematics evolved something smarter: visual representation. A pictograph transforms numerical information into visual symbols. One symbol may represent one object, or 10, or 50, or even 1,000. And now the real challenge begins: choosing the correct scale. Imagine a village selling 425 kites. If one symbol represents 100 kites, 4 symbols are not enough. So mathematicians introduce partial symbols, half symbols, quarter symbols. Precision matters because a misleading visual can create a misleading conclusion. This is exactly why pictographs become difficult for extremely large datasets. When frequencies are not exact multiples of the scale, representation becomes mathematically delicate. And that leads us to one of the most powerful tools in data science: bar graphs. A bar graph converts frequencies into heights or lengths. One glance, and the brain immediately identifies maximums, minimums, comparisons, and trends. This is why newspapers, scientists, economists, and analysts constantly use graphs. Consider traffic flow across a major city intersection. At 6 a.m., traffic is minimal. By 7 to 8 a.m., the graph suddenly spikes upward. Without reading every number individually, your brain instantly detects peak congestion. That is the true power of graphical interpretation. Graphs compress large quantities of information into immediate visual understanding. But drawing a graph is not enough. A mathematically correct graph depends on scale. If values range from 0 to 4,000, using 1 unit for one value becomes impossible. So, mathematicians choose intelligent scales. 1 unit may represent 10, 100, 1,000. The scale must balance accuracy, readability, and space. And there is another important rule. A professional graph always begins from 0, because manipulating the starting point can visually exaggerate differences. The data remains unchanged, but perception changes, and that can completely mislead the audience. Bar graphs also follow strict structural principles: uniform width, equal spacing, clearly labeled axes, consistent scaling. These are not artistic choices alone. They preserve mathematical accuracy. Now, let's push the thinking even further. Suppose a graph shows India's population across decades. You are no longer simply reading numbers. You are analyzing growth, predicting trends, comparing rates of increase. This transition from observation to inference is where real mathematics begins. The chapter also introduces artistic and aesthetic considerations in data presentation. A good graph is not only correct, it must also communicate clearly. Tall mountains are better represented using vertical columns. Why? Because the visual structure itself reinforces the meaning. When graphs become intuitive, interpretation becomes faster. This chapter may appear simple at first glance, but beneath tally marks and bars lies a deeper mathematical idea, transforming chaos into clarity, collecting information, organizing it intelligently, representing it visually, and finally, extracting meaning from it. Because mathematics is not merely about calculation. It is the science of discovering patterns hidden inside information. The world gives data to everyone, but only trained minds can convert data into understanding.